Hi, I am Selva. In this one, we will see Bayesian target encoding, the concept behind Bayesian target encoding in very clear and complete detail. We will also see 4 other different techniques to overcome the problem of data leakage and subsequently the overfitting that it causes in target encoding. So previously we saw this powerful method called target encoding that is used for encoding categorical data into numeric data so that it can be used for machine learning algorithms. Remember, if you have not watched that earlier video or have no context about what target encoding is, you might want to check out that video first before starting this. I will leave a link in the description if you want to know more about that in detail. Nevertheless, we will quickly summarize what target encoding is and the problem of data leakage quickly, and then we will jump into Bayesian target encoding right now. Alright, so let's get into this. So here we have 2 different variables. We have gender and exit. Imagine these are different customers. The genders of different customers are captured, and whether that customer has churned or exited from the business or not, that information is also captured. This is a sample data, of course. Now, to do target encoding on this, what we would do is we will simply compute. So for all the males, we have males and females. For all the males, we will compute the mean of all the males, and substitute that mean wherever m occurs. So in this case, we have 1, 2, 3, 4 instances. 4 instances. So you have 1 plus 1 plus 1. So you have 1, 1, 1. 1 plus 1 plus 1 plus 0 divided by 4. So the mean would be 3 by 4. Isn't it? So wherever m occurs, we will replace those m's with 3 by 4, 3 by 4 and so on. And wherever there is a female, so you take the mean of females, that would be, you have a 1 here and you have a 0 here. So 1 plus 0 by 2, that would be 1 by 2. So wherever female occurs, we will replace it by 1 by 2. 1 by 2. Now if you think about it, we have simply replaced the respective categories with the probability that that particular category will exit. So these numbers here represent the probability that a given male would exit, isn't it? It represents the probability. Now the problem here is we are actually using the data of what we want to predict. So this is the y. This is the variable that we want to predict. We want to use x, and some other x also might exist in the real world data. In this case, we are taking only one x, one predictor. Alright. So we are using x to predict y, but in this one, we are constructing a new form, a target encoded form of x that actually is constructed using the y. Isn't it? So that is what we normally refer to as data leakage. Data leakage. We can still use this information, use this data, use this column that we have created to build your machine learning model. And for newer data, right? So to make predictions for new data, suppose a new male comes here, new female comes here, new male comes here, alright? We will only know these categories. We want to predict, use the machine learning. So this is an input. This is the input. This is output, right? You pass the input to ML. The ML would have already learned from this data, alright? So it embeds, or it has learned from this, so it's probably an equation or something like that. So you pass the input to the machine learning algorithm, and that is going to give the output, which is nothing but whether a given customer has churned or not. That's how ML works. Now in this case, we are going to simply replace all these. Suppose if it is m, we are going to replace it with 3 by 4, and if it is female, it's going to be 1 by 2. Alright, we're going to use this information to predict the y. So prediction is still possible. We can still use the target encoded version to make our predictions into the future. Alright, this is possible, but the problem of data leakage, right? What happens is, for newer data, this distribution in this data, the probability that a given customer is going to churn was 3 by 4. Alright. As you accumulate or as you gain new data, this probability can change with time. Right? This can become, say, 2 by 3. It can become, say, 4 by 7, something like that. With time, this probability ratio can change. Agree with me? So that can cause, so your model here, your machine learning model is going to perform really well on training data. The performance of the model will be really good on training data, but not on data that it has not seen in the future. You can expect a drop in the performance of the model on the data it has not seen. And with time, with time the performance can deteriorate. That means, so it does well on training data but not on future new data, right? That is leading to this problem of overfitting. Alright, this is the whole context. This is what target encoding is, and this is the problem with target encoding. I just described that. Now, how to overcome this? There are multiple different approaches. We have leave one out method, time ordered method, and so on. Alright, we will look at these methods one by one. Each and every one of them is going to be really interesting. Alright, the last two ones, these are the two different versions of Bayesian target encoding. We will look at this also. All of it is going to be super interesting. After looking at this, we will also see how to implement these methods, especially the last two methods, using Python. Alright, using in Python code, using scikit-learn and one other new package. We will look at all those aspects. Alright, so what is leave one out method? The very first approach is leave one out method. Now here you have this data. Now if you want to compute the target encoded version of this particular instance, alright, to compute the target encoded version of this particular instance, what leave one out method will do is to compute the mean encoding, it will not consider this particular row. It will not consider this row. Let me put in a different color. It will not consider this row and compute the mean encoding for this row from rest of the data, remaining 5 rows. So here, look at this. You have one m here, another m here. So that would be, so the target encoded version would be 1 plus 1 plus 0 by 3. That would be 2 by 3. Alright, for this particular row. Likewise, for here, when it comes to this particular row, you will leave this one out, this one alone out. This will get again included. Here anyway, this is going to be m, so we will not use it. But suppose if this was f, then we will include this row also for computing the second row here, this particular row that we are doing here. So in this case, ignore this. Remaining, we have just one instance of f. So 0 divided by just one instance, right? So the mean here is going to be 0 by 1 is 0. Alright, for this particular row. Alright, not this row, sorry, not this row, for this row. Second row, we have 0 by 1, which is 0. Alright, let me erase this. Likewise, if you want to do it for this row of f, you will ignore this row, you will strike out this row, ignore this row, and we will include this row, the second row. We will include the second row. This will count. So here in this case, we have one instance of f equal to 1, just one instance, and out of that one instance, so 1 out of 1 is present. Alright, so the mean encoded version of this particular f would be 1. So not all the f cases, not all the different occurrences, different rows will have the same value. Alright, now if we compute for m, right, we will leave out this particular row. We will include this guy, and this guy. So that would be 1 plus 1 plus 0 by 3. That is this one, and this one by 3 equal to 2 by 3. So that is leave one out encoding method. The next method is the time ordered method. Now if there was a time element, imagine there was a time element here, is time t1, t2, this could be first day, second day, third day, or it could be monthly data also, we don't know that. Imagine there was a time element, alright. Here when computing the mean encoding for any particular row, we will include only the data for which we know the answer for. Alright, so suppose if you want to compute the mean encoding for this particular row, the fourth row, at this point, we would have the data, only these 4 observations will be present, isn't it? Only these 4 observations will be present. So we will not include these 2 rows, the last 2 rows. Likewise, when you compute for this particular row, the third day, time t3, only the first 3 observations will be considered. Only these first 3 observations will be considered. Alright. Likewise, for 2, only the first 2 observations. For 1, that's just the first observation. So imagine now, if you want to compute the mean encoding for m, we will have the mean of m, one m here, another m here, another m here. So all three cases are 1s. So 1 plus 1 divided by 3, you have perfect score of 1. Alright. So for this m, you will replace it with 1. What about this m? We will have all these records. So 1 plus 1 plus 1 plus 0, that would be 3 divided by 4. You will replace this particular m with 3 by 4. And this approach makes a lot of sense, isn't it? It is almost like a real case. So at this particular point, you don't know the future value, so you're not including them in computing the means. Now, this approach is also the foundational approach for CatBoost algorithm. CatBoost is a very famous machine learning algorithm known for its high performance capabilities. It generally produces, its predictions are usually more accurate, right? Now, inside CatBoost, this algorithm also handles the target encoding using a method something similar to what we just saw, only that even if there is no time element involved, CatBoost will assume this time orderedness. It will introduce a random order, a randomized order. It will introduce a randomized order and then compute the mean following the exact same method, only that instead of time, it will just introduce an order 1, 2, 3, 4 and all. It will first randomize the entire data and give an order to it and then compute it based on this approach only. So if you want to compute it for the row 4, it will take only this part of the data. Same approach. Getting me? So this whole operation for one iteration, right? So this will do it, this randomization will be done, randomization and computing the mean will be done for multiple iterations, not just one iteration. So it will do one instance of randomization, compute the mean encodings for all the rows, alright? And it will keep on doing this for multiple times and take the mean. So this is first iteration, second iteration you will have another set of mean encodings, third iteration you will have another set of encodings for all the rows, alright? It will take the mean of all these rows and uses that mean as the final category encoded version or target encoded version of each of these categories in the data. That's what CatBoost does. That's the fundamental foundations of what CatBoost does. Excellent approach again. Alright. Now, the third method we have here is the k-fold method. This is also very similar to the leave one out method, only that in k-fold, you will define the value of k. Suppose k was 5, we will split the entire data set into parts of 5 parts of equal sizes. Alright, so if k was 5, so suppose if there was 100 rows in the entire data, you will split this 100 rows into 20, 20, 20, 20, 20. 5 different parts of, say, this will be 20 rows, 20 rows, 20 rows, 20 rows, 20 rows, randomly split, and to compute the mean encodings for this particular row, this particular set of rows, this entire chunk, this is called fold 1, fold 2, fold 3, 4 and 5, alright. This entire fold will be left out. It will be computed, the ratios will be computed, the means will be computed on the remaining set of the folds, remaining 4 folds, right, and that will be used to replace these gender values here. Alright, the same approach is done for the remaining folds also. Alright, so the values of the means here in this fold will not be the same in the second fold, but within the second fold it will be the same. If you have a male here and another male here, within the second fold the values of these two males will be the same because this entire fold is not taken into consideration when you are computing the mean encodings. Alright, that is what the whole concept is behind k-fold method of target encoding. Alright, this is also a way of overcoming this problem of overfitting. Alright, good. The next method that we are going to look at is additive smoothing. This is very popularly used by the IMDb, Internet Movie Database. This is a very popular movies ratings website owned by Amazon. Right? IMDb uses a certain method to rate movies. So imagine this case. You have a movie A. You can consider this as to be any popular movie, right? Right after releasing the movie, you will have lesser number of votes. You have another movie B which has a lot of votes, 10,000 votes, and the average rating for this movie is 8.9. Let's say, all right. So for movie B, we have a good number of votes, and average rating is 8.9. But movie A, it just got released, very new. it has just 3 votes. Alright, and these 3 votes are 10, 10, 10. Now between this, if you take the average of movie A, the average is going to be 10, isn't it? Now this has an average of 10, whereas movie B has an average of 8.9. Does it mean that movie A is a better movie than movie B? Not yet. It has not proved itself yet. As you get more ratings data coming in, this average can go down. It can go down, right? Now, how would IMDb rate these movies? Would it show movie B above the ranking in terms of compared to movie A or below it, right? How does Netflix adjust for this uncertainty? So instead of showing the raw average of the movie A, just average as 10, what Netflix would do is it does an adjusted rating, it computes an adjusted rating based on this particular formula. So you have n divided by n plus m into r, capital M divided by n plus m into capital R. So what are these terms? N is the number of ratings that this movie got. Alright, so adjusted rating for movie A would be, in this case, n is the number of ratings, number of votes this movie got. So in this case, small n would be 3. Isn't it? For this movie A, small n would be 3. This is also 3. Alright, and small r is the movie rating, average movie rating for movie A. In this case, small r is nothing but average is 10. This value is 10. So this guy is 10. Alright, so we know this value, this is fine, this is fine. What is m? M is the total number of votes for all the movies. This is the minimum, it is considered as sort of a baseline of the minimum number of votes that needs to be present. Alright, this is a set number. In case of IMDb, the minimum threshold votes that IMDb took in order to give a proper rating for that movie, at that time it was 1250. Now the reference for this particular link, I'm not able to find it online. Previously this used to be published in public, but only in forums they talk about this, not on any official forum that was published by IMDb. And we are not able to find that page, otherwise I would have linked that page here. But long time back when I studied about this, I found that page in Netflix actually officially published this approach, but I'm not able to find that link anymore. Anyway, so here, this is the minimum number of votes at this point, and small n we know, capital M we know, small r we know, and capital R is the overall rating for all the movies that exist in Netflix or IMDb in this case. Sorry about this. So capital R here is, at that particular point in time, the average rating for all the movies was 6.9. So now we know, okay, this would be capital M, this would be capital M. So we know all these values. You can simply substitute it and get the adjusted rating. Now for this, can we substitute this? So small n would be 3 divided by 3 plus 1250. Capital M is minimum votes is 1250, multiplied by 10, average rating is 10, plus capital M here is 1250 divided by 3 plus 1250 multiplied by, what is this number? 6.9. Alright. This would be the adjusted rating. Now the value of this whole number turns out to be 6.9074, which approximates to 6.91. Alright. So this movie A is doing slightly better than the average. So average rating was 6.9. It has got only 3 votes. As it gets more and more number of votes, a better vote than 6.9 of course, as it gets more and more votes, the adjusted rating of movie A is going to improve. Alright. Now this exact same approach is what we are going to be doing in mean encoding. Exact same approach. Now the effectiveness of this, right? So suppose here, if we had, say, instead of 3 votes, suppose we had 10 votes that had 10, like 10 votes of 10 rating, right? This number will slightly improve to 6.92 with 10 ratings. with 100 ratings you can compute, right? As you get more and more ratings, this is going to, so this rating is going to move towards 10 gradually. So now when applying this to mean encoding in terms of category encoders, in applying this to mean encoding, this is going to be the formula. Exact same formula, like number of observations of that particular category, total number of observations, M is the total number of observations, right? So we know this. R would be the mean of that category, mean of that particular category value. That would be the small r. Capital R is the overall mean. Capital R is the overall mean. Now let's imagine if you have a particular category, say the male and female, right? Male and female we saw earlier. If there were only 3 males and totally say 10,000 females that exist in the data, right? In that case, the mean encoding for the male in this case is going to be 3 divided by 3 plus, this is 3, total M here in this case would be 3 plus 10,000. So 3 plus 10,000 would be 10,003, right? So this whole term is multiplied by small r, whereas the right hand side term, right? So that would be 10,000 divided by 3 plus 10,003 would be 10,006 multiplied by capital R. So as this M increases, total number of observations increases to a very large number, as well as the number of observations for that category is small, right? Observations, the number of categories is small, then this whole mean encoding is going to go towards the overall mean, which is capital R here. So what this means for us is, in Bayesian target encoding, the feature encodings of the different categories are driven towards the mean of the entire global, towards the global mean, all the categories considered together, right? The individual categories means are driven towards the global mean, and if an individual category is very different from the global mean, in that case only for those categories alone, their feature encodings are going to be different. That's the whole idea. That's the whole idea of creating the Bayesian target encoding itself. Now, an alternate formula to implement the same Bayesian target encoding is this. So you have the category mean, you have the whole global mean, small r and the capital R, and you also have, in this case, previously you had small m divided by n plus capital M, right? Instead of that, you have an alpha term. The formula for this alpha term is given by this equation, where the n in this equation is the number of records for that particular category, and the values of k and f are actually hyperparameters which can be determined. So I will leave a link. I will show you how to read more about this particular parameters, the more details into the explanations of these parameters. But if you're not sure, you can simply keep it as 1 and 1. Both value of k and f, you can set it as 1 and use this formula, right? Alternately, you can let the algorithm to decide what the values of k and f are based on this particular paper that I'm going to link here, I'm going to show here, is based on this particular paper, a pre-processing scheme for high cardinality categorical attributes in classification prediction problems. So this is the base for the formula that we just saw here. Now you don't have to manually implement this. This whole approach, this particular formula is implemented in the Python package called category encoders, and you can implement this version of additive smoothing, Bayesian encoding, from scikit-learn itself, sklearn, the scikit-learn package directly. Now how to implement this? Now in order to use this in scikit-learn, you have to use the nightly build of scikit-learn, right? This is not available right away in the main version, the stable version of scikit-learn. In order to use this, you need to install the latest version, which is at this point is version 1.2. In this one, in order to install the nightly version, you need to run this particular command. Okay, if you go here, if you search for target encoders and you find this this object or this kind of a notification to be present, you click on this link, install the nightly version, you click on this link, it will open this page. Here it is mentioned what is the command that you will need to use in order to install the nightly build of scikit-learn. Alright, once you installed that, then this particular object will be available to you, target encoder. From scikit-learn.preprocessing, you will have the target encoder class. By using this class, you will be able to implement the Bayesian target encoder that we just saw. So to implement this is quite straightforward. You can, after you install nightly build, of course, you will be able to import target encoder. Then you have the X and the Y. This can typically come from your dataset, whichever dataset that you are using. Then use target encoder smooth equal to auto, right, default setting, and use a fit transform to get the transformed version of the categorical data that you have here. So the transformed version of dog, cat, snake, all these objects is going to be present in a numeric form in this data. Now this lets you control how much weight you want to put for the global mean versus the target mean, right? If you want to put more weightage for the global mean, you can set smooth equal to a very large number, and that will give more weightage towards, so all your feature encodings will be more towards the global mean of the categorical data. Alright, if you want to give more weightage to the specific categories, individual categories means, then you want to set this particular smooth value to be a very small number. That way you can control how much of smoothing that you want to do with target encoder. Alright, so this is very nice implementation of doing this. There is also another very powerful package, the latest version that we saw, right? The additive smoothing here based on this alternate formula. This you can implement using the category encoders package. We are in the page of category encoders. In this package, you have a class, the category encoders, target encoder class. You can use this class. Let me zoom this in a bit. Okay, you can use this particular class to implement the newer version of additive smoothing. In the bottom of the page, we have an example code. From category encoders dataset, we are importing the load compass dataset. X and the Y is imported. Now target encoder, this is the object that we will use to do the target encoding. Now here, you can control how much you want to go towards the global by setting the smoothing parameter here also. Right? So this will be the encoded values. You can use enc.transform to get the actual values. The actual encoded values is stored here. And hierarchy dataset compass.values is going to print out the values of the encoded version of the categorical data. So that's how you can implement both of these Bayesian target encoding approaches. Very powerful, very useful. So next time you are working with a categorical data in your machine learning project, please consider using these approaches and see how the performance of the entire model is going to turn out to be. Alright, so based on that, you can choose which is the best performing or which is the optimal way of encoding your categorical data. If you are in doubt, just implement the scikit-learn version, or this also is fine. Try to implement one of them and see how it is affecting the overall model's performance.